Well, this is the last of the recordings that I have to make for this course, and with the way things have gone today, I'm kind of glad it is, because it took me a couple takes to make 7.1 and 7.2, and now this is like my second take on this one, because of technical errors that kept getting in the way. So, I myself am kind of glad that this is the last recording I had to make, because that process will be done. But we deal with Lagrange multipliers and constrained optimization, which makes it sound like it's a much more difficult thing that we've done before. It really isn't. It's just a different method of doing optimization, because the optimization we had been doing before was actually a constrained multiplication or optimization. And when we get to the first example, I'll kind of go into that a bit more. Now, as we come up with these constraints, and you're often going to be given a constraint, by which you're going to find a maximum and or a minimum for a given function with two variables. And it's going to tend to be two variables, although there are procedures you can do for more variables. It just would take considerably longer. So, you're going to be given a function that's going to be called your objective function. And you're going to be given a function that's going to be called your constraint function. The constraint function is always going to be set equal to 0, and g of xy is your constraint function. So, this is getting to kind of, and then we're going to kind of show you how to do this via an example. An example that you've used before and we've done before, and you're able to do with other methods, including one variable calculus or even using quadratics, as we're dealing with area. So, very typical type of problem that you see in many textbooks. The farmer wants to build a rectangular enclosure along an existing stone wall with the side of the wall needs no fence. Find the dimensions of the largest enclosure that can be made using only 400 feet of fence. So, we would start, using the newer method and using the older method, we kind of always start off the same way. We would let, length times width. Here we're saying x times y, which I always tended to avoid, because, if you're looking for a graph, and we tend to kind of consider the graph as we were maximizing the area, because we would eventually come up with an area function in terms of a single variable. And when you graph it, you would get some kind of parabola. Well, this is your x, and this is actually your a. The y was the a. And so when students tend to put y as the second, dimension, they start thinking that whatever y coordinate they're getting is the dimension instead of what the area would be, and having to calculate what y is with respect to this equation. But be it as it may, since we're using kind of a multivariable approach, and we really don't need to graph it for the circumstances we're being given, we're going to kind of look at this and say, okay, well, I know that 2x plus y would have to equal 400, because you can see that the way I labeled them, I have 2 x's, 1 y, they total 400 feet of fencing. That's my constraint function. And I would often just set this equal and say, well, y equals 400 minus 2x, because I know that the area of the function, or the area, is going to be x times y. And what I would tend to do at that point is, here I'm going to substitute the y for the 400 minus 2x. I would end up with my equation. Negative 2x squared plus 400. Now, I could either use a derivative and set that equal to 0 to find my critical point. I could then use various methods to determine whether it's a maximum or a minimum. Or I can recognize this is a quadratic function. I have a leading coefficient of negative 2, which means this is going to open downward and have a maximum. The maximum is going to occur at x equaling negative b over 2a. And if I put, the 400 in and the negative 2 in the right spot, I do get 100. Which means that x equals 100. I would then come back up here and say, well, 400 minus 2 times 100 would give me 200. So that would be my other dimension. So I could say that the enclosure would need to be 100 feet by 200 feet to maximize the area. They don't say what they want. If they want us to find out what the maximum area would be, I can figure that out pretty easily. You're talking about 20,000 square feet. Once I know the length and width, that's pretty easy to do. But how do we do it with the newer methods that they're asking us to do here? Which it's basically the reason why you're being taught this here is because if you have to go into more sophisticated math and use Lagrange multipliers, there's some instances where it's going to be much easier to do. Whereas with the situations you're going to be primarily asked to do in this course, that's going to be a wash. I'm not going to necessarily say it's going to be easier. It might actually take longer to do, but I just want you to get used to the procedure. So I kind of start off the same way. I come up with my function here, and I still recognize that the area function is x times y, and it's subject to the constraint function 2x plus y minus 400, which is set equal to 0. So this is my constraint function, g of x. This is my f of xy function. That's what we call the objective function. I'm going to make a Lagrange function, which is capital F, x comma y comma lambda. So I'm making basically a situation that has two variables. I'm making it a 3-variable function. And the way I do this is I take this here is going to be, and you'll see this formula on another slide. So if you don't catch it here, if I can get the pen to work again, plus lambda times g of x. So that's why we said this was g of x before. This is my f of x function. And so I come up with this function. I distribute to multiply it all out. And now what I'm going to do is I'm going to find partials for each of the 3 variables. The 3 variables being x, y, and lambda. So if I take that function and find the partial derivative with respect to x, I get y plus 2 lambda. If I take the partial derivative with respect to y, I get x plus lambda. And ultimately, if I take the function and the partial derivative with respect to lambda, I would get back to essentially g of xy again. Or you might get basically the opposite of g xy at that point. And then you can just multiply both sides by -1. You're back, because -0 is still 0. So now they always recommend solving for lambda. Put lambda in terms of y, put lambda in terms of x. And in some cases I agree with that if it's easier, but in this circumstance, I'll show you what they eventually do, but I'm going to show you what I do first. This one here, I could see that y would equal 2 lambda. I could see that x would equal lambda. So when I come down to this function here, I'm going to have 2 lambda plus 2 times 2 lambda equaling 400 if I put the minus 400 to the other side. And that's not a 2 times 2 lambda, it's just 2 lambda. So I'm going to have 4 lambda equaling 400. Which means that lambda is going to equal 100. And if lambda equals 100, x equals 100. And if y equals 2 times lambda, it's going to be 2 times 100, which equals 200. They instead, they solve for lambda. They get lambda in terms of x or y. So for the top equation, they get that lambda equals -1/2 y. The other one is that lambda equals -x. They set these equal to each other. And they say that basically, y equals 2x, and then they do a substitution. So you're still eventually getting the equation in terms of one variable. So you're still doing one variable methods ultimately, even using Lagrange multipliers, which again kind of makes it seem like, well, why do we do this if we could use single variable methods anyway? Again, this is something that works better for bigger circumstances. Lagrange multipliers at this level, though, have a lot of issues that we're going to talk about some more in a moment. But this just shows you they get the same values that we got before. So 100 feet by 200 feet is what the dimensions of the wall need to be. So here they talk about the objective function. That's your f of x, y, your constraint function, your Lagrange multiplier. Here's the formula that I showed before. The Lagrange function is equal to the objective function plus lambda times the constraint function. You set these equal to 0, and then you solve the original problem. Here's some of the issues about Lagrange multipliers. The Lagrange method only finds critical points. It doesn't tell you what they are. Whereas we had methods beforehand that we could find that critical points, and then we could determine using a d-test if it's a maximum, a minimum, or a saddle point. The Lagrange method doesn't do anything about that. In each problem, we must know that the maximum or minimum, whichever is requested, does exist, and it then follows that it must occur at a critical point. So there's a lot of what-ifs here. So how do we know that the maximum or minimum does exist? And they say, well, the most reasonable applied problems do have solutions. Using the word most does not make it seem all that reassuring. In example 1, basically, since we have a limited number of fence, there's going to be, a biggest amount of area we can enclose using that fence. That's just, that's kind of a logical standpoint. So it's going to have a maximum. The problem with that is knowing it exists and making sure that you're reaching the conditions needed to find what it is. They don't always match up. As I mentioned before, we had methods before. If I'd used multiple variable methods we learned in lesson 3, I could run a d-test and verify that it's a maximum. If I go back to using single variable methods, knowing the way that the function behaves, knowing it reaches a maximum, knowing how to find that maximum, there's ways for me guaranteeing what's going on. So if I end up with a function that doesn't do that, that was always an indication, well, I might be doing something incorrect. So you kind of lose that with this. Its advantage is that it eliminates the need to solve the constant equation, the constraint equation, which can sometimes be difficult. Unfortunately, the circumstances you're going to be given are not necessarily going to make that the case. You might give some examples where you really can't solve it, but in some of the practical circumstances, you're going to probably be able to solve it. And it is symmetric in the variables, thereby allowing you to solve for whichever variable is easier to find. So it's your turn. You're given a constraint equation here. And you're being asked here to find the maximum value for f of xy being 12xy minus 3y squared minus x squared, where the constraint equation is x plus y equaling 16. And here they are telling you that the maximum value does exist. So if you find a critical point, it should by logic be the maximum. So go through the steps to figure out what that is using Lagrange multipliers and present your answer at this point. So, my objective function we were given. My constraint function is just the constraint equation set equal to 0. Therefore, my Lagrange equation, or my Lagrange function for this circumstance is going to be 12xy minus 3y squared minus x squared plus g of xy, which is just going to be x plus y minus 16 times lambda. So I get 12xy minus 3y squared minus x squared plus lambda x plus lambda y minus 16 lambda. So that's my Lagrange function. Now I'm going to find my three partials. So my three partials are going to be fx, which is going to be 12y minus, or no, take that back, 12x. No, 12y. The 3y squared is a constant, so it's going to become nothing. The minus x squared is going to become a minus 2x when I take the derivative with respect to x, plus lambda. The lambda y and the 16 lambda are going to become constant, so they become 0. And I will eventually set that equal to 0. The partial with respect to y is going to be 12x minus 6y. The x squared and the lambda x are both constants with respect to y, so they're going to become 0. I'm going to have a plus lambda. And the 16 lambda is another constant, so that's set equal to 0. And of course, f, partial derivative of f with respect to lambda, is just going to get me back to my g of x function again. So what I'm going to do with these two, again, this one here, I mean, because I still have x's and y's involved, I'm going to solve this for lambda. So lambda is going to be 2x minus 12y. Here lambda is going to be negative 12x plus 6y. And because these both equal lambda, I can set them equal to each other and say, well, 2x minus 12y is going to equal negative 12x plus 6y. If I add 12x to both sides and add 12y to both sides, I get that 14x equals 18y. And I could say, solving for x, I get, divide both sides by 14. 18 over 14 reduces to 9 over 7. Y. So now I have one variable in terms of the other. So if I come down to f of the partial derivative with respect to lambda's formula, I'm going to have 9/7 y plus y minus 16 equaling 0, which is going to give me 16 over 7. Take that back here. (16/7) y equaling 16. And then when I multiply both sides by 7/16 to get y alone, I end up with 7 over here. Which means if I go back to this function up here, in particular, which is the same thing as f lambda, and I plug in the y, I get x plus 7 minus 16 equaling 0. That means that x minus 9 equals 0, so x has to equal 9. So I know I have a critical point at 9/7. And since that's the only critical point I have, and the fact I'm using Lagrange multipliers and we're assuming it's going to have an answer, that is where the maximum is. So the maximum value of f of xy is at 9.7, and the maximum and is equal to f of 9.7, which is, and that means I'm just going to come back up here and say, well, 12 times 9 times 7 minus 3 times 7 squared minus 9 squared. And when I work that out, I get 528. So it does have a maximum value at 9.7, and that maximum value is 528. So some hints for solving partial equations, which I kind of demonstrated as I went through it. You solve, you solve each partial derivative f of x and equaling 0, f of y equaling 0 for lambda. In general, that's the case. It's usually going to be the easier method. You set the two expressions equal to each other, once they're in terms of lambda. And then you're going to solve the equation resulting from step 2 to find x and then or y, and then once you've found what that is, you go back and figure out what the other one is. So designing a most efficient container. So like here's an application problem. They give you a container that's to hold 12 fluid ounces, or about 21.3 cubic inches. Find the radius and height of the can, where you're using the least amount of material, but will definitely hold that amount. So minimizing the amount of aluminum means minimizing the surface area. So the surface area of a can, including the side and the two lids, the top and bottom, is going to be 2 pi r squared plus 2 pi rh. The volume is pi r squared h, and we know that's supposed to equal 21.3. So this area function here is our f of xy. If I take this and subtract 21.3, set equal to 0, this is my g of xy. So when I apply the Lagrange equation, here's my f of xy again. Here's my lambda times g of xy. They don't show all the simplification here, but the partials you would get as a result, and some of it's running into each other because of the fact that I have these things in the way, so I'm just going to get these out of the way. The partial derivatives would be as they're defined here. I don't end up with any particularly easy functions to look at here, so the best way would be to solve these first two equations in terms of lambda. So for the first one, lambda would be negative 4 pi r plus 2 pi h all over 2 pi rh. If you do simplify a little bit, because all terms on the top and bottom are divisible by 2 pi, I would end up with 2r plus h over rh. When I do this, the second one, the f sub y, or f sub h, I end up with negative 2 pi r over pi r squared. Again, both are divisible by pi r. So I need negative 2 over r. I set these equal to each other. When I cross multiply, and what they don't show you here, I'll kind of do it to this side, I'm going to end up with r r times 2r plus h equaling 2 times r times h. both have a multiplication of r that can be canceled. So that's why they end up with 2r plus h equaling 2h. And then I could solve both sides. I could solve this equation. 2r is going to equal h, which means I could go to my volume equation, which is my constraint equation as well, and say and replace h with 2r. I would get 2 pi r cubed equaling 21 over 0.3. I would divide both sides by 2 pi, and then I would cube root, and I would get about 1.5, which means that the height would be about 3. So the most economical can would be a radius of 1.5 inches and a height of about 3 inches. So now your turn. You have 3 adjacent rectangular lots to be fenced in as shown in the diagram below. Fencing in the lot will require 12,000 feet of fence. What is the largest total area that can be enclosed? Keep in mind that you have, the perimeter of the fence and you have the 2 partitions in there. So, all that's being built with that 12,000 feet of fencing. Okay. There's different ways to approach this problem. It really depends on how you're defining your x's and y's, but you have to keep track of how you're going to compute the area ultimately, and what your variables are going to represent. I'm going to kind of draw more of an aerial view of this because I'm only concerned about the area it's enclosing. And I can assume these are equal sizes. They don't necessarily have to be, but the important part is, these partitions should have the same length as, the sides of the rectangle. And this other length, and I'm not calling length and width because I don't know which one's going to be longer in the long run than the other. I'm just kind of drawing it this way to kind of say, okay, that's what it may or may not look like. I don't know yet. It really doesn't matter for this. I'm just trying to figure out what the maximum area needs to be. So, the area, the way I'm defining x and y, is just going to be x times y. I know that 1, 2, 3, 4 x's plus 1 y, and I'm also going to have another y up here, 2 y's, which would represent the kind of like the perimeter, more or less. Sort of the perimeter. The perimeter would usually just be the outside, but since I have some partitions, I got to include that. But that's going to be essentially the 12,000 feet of fencing I'm going to use. Which means essentially that g of x, y, is going to be 4x plus 2y minus 12,000. And this up here is going to be my f of xy. So when I do my Lagrange function for this, f of x, y, lambda, I'm going to have xy plus lambda times 4x plus 2y minus 12,000, which is xy plus 4 lambda x plus 4 lambda y, or 2 lambda y, minus 12,000 lambda. So now I'm going to find my partials. So I have my partial derivative with respect to x for my Lagrange function. That's going to give me y plus plus 4 lambda The 2 lambda y and the minus 12,000 lambda are constants, so they're gone. That'll be set equal to 0 at some point. My partial derivative with respect to y is going to give me x. The plus 4 lambda x is going to be a constant, so that's going to become 0. The 2 lambda y is just going to become 2 lambda. And again, the minus 12,000 lambda is a constant, so that is my f of y. I'm going to set that equal to 0. And of course, f of lambda is just going to be my g of x function, xy function again. So I'm going to have 4x plus 2y minus 12,000 equal to 0. Again, I could solve these both for x and y, and solve these both for lambda, but in actuality, again, I think it's easier if I just say, okay, well, y is going to be a negative 4 lambda, x is going to be a negative 2 lambda, which means, give me a second here, yeah, that when I do f sub lambda, I'm going to have 4 times negative 2 lambda plus 2 times negative 4 lambda equaling 12,000, which means I have negative 16 lambda equaling 12,000, which when I divide both sides by negative 16, I get that lambda equals a negative 750. So for our cases here, negative 4 times negative 750 is 3,000. X being negative 2 lambda is going to be negative 2 times negative 750, which is 1,500. And these are in feet. That would be the dimension. I'm not looking for the dimension. I'm looking for the largest total area enclosed. Always make sure that you are answering the question. Now, again, since we use Lagrange multipliers, I didn't have, I didn't do any. I can't do any kind of check to see if this is indeed where the maximum would be, and that's the way it would be defined. But I can assume that this is the only critical point I have for x and y. And since we are assuming that because it's a reasonable answer, I have a limited amount of fencing to use, that there's going to be a biggest possible area I can enclose. So it's a reasonable answer to assume that I can reach a maximum. This is where it would be. So my maximum area would be the maximum area is going to be f of 1,500 comma 3,000. And so when I plug that into the function right here, I get 4,500,000 square feet. So that is the maximum area, or the largest total area I can combine. They go into the meaning of the Lagrange multiplier here. Again, interesting reading, I guess, depending on your point of view. You can get situations, though, where you may have several critical points. The maximum and minimum values, which we assume to exist, are the largest and smallest of the resulting values of the function. So if we use Lagrange multipliers, that's how we determine if it's a maximum or a minimum. Whichever ordered pair produces the largest value for your objective function is the maximum. The one that produces the smallest is the minimum. We're assuming that these are all reasonable answers for the circumstance that we're given. Again, that's a lot. That could be a stretch, but that's what's going on with this. So for example 3 here, we're looking to maximize and minimize f of x, y, and it's subject to the constraint x squared plus y squared equals 50. So again, this is going to be my objective function f of x, y. This here, if I take this is set equal to 0 and solve it that way, this is g of x. So when I set up my Lagrange function, I'm going to have 4xy plus lambda times x squared plus y squared minus 50. When I do my partials, here's what they are. They don't show all the, the simplification along the way, but you could go through and make sure that's what you get. They solve both the f sub x and f sub y in terms of lambda. You end up with this function here, which means that 2y squared would equal 2x squared. Y squared would equal x squared. And there's a couple of situations. So y is going to equal plus or minus x. And so if I plug this into my constraint equation, I would get that, essentially x could equal 5 or negative 5. Y could equal 5 or negative 5. So what I'm going to get here is I'm going to get 4 critical points. 5, 5, 5, 5, negative 5, negative 5, 5, and negative 5, negative 5. Those are my critical points. And so if I put them into the function 4xy, at 5, 5, and negative 5, negative 5, I get 100. At 5, negative 5, and negative 5, 5, I get negative 100. So these two would be relative maximums because they reach a maximum value. These are relative minimums. If one of these two, for instance, was higher than the other, then I would just say, okay, then I have the highest. The one would be the highest value. The other one would be, okay, still relative, but not the absolute. So, your turn. Use Lagrange multipliers to maximize and minimize each function subject to the constraint. The maximum and minimum values do exist. So, I have my f of x, y. If I take this and set it equal to 0, this is my g of x, y. So my Lagrange function is going to be 2xy plus lambda times x squared plus y squared minus 18, which is 2xy plus lambda x squared plus lambda y squared minus 18 lambda. Now doing my partials. Partial derivative with respect to x is going to give me 2y plus 2 lambda x. The lambda y squared and the minus 18 lambda are constants with respect to x, so there will be zeros when I differentiate. The partial derivative with respect to y is going to be 2x. The lambda x squared is going to be a constant, so I treat that's going to become 0. I'm going to have 2 lambda y. And the minus 18 lambda is a constant again, so that becomes a 0. And of course, f of lambda. Again, this ends up being the g of x, y function I come up with, and that's because the 2xy is a constant. everything else, the lambdas are just going to basically disappear when I differentiate. And these are all set equal to 0. In both cases, I get that essentially lambda equals 0 equals 0. 2 lambda x is going to equal a negative 2y, which means lambda is going to be a negative y over x when I solve the top one, or f sub x. When I solve f or the partial derivative with respect to y, I get that 2 lambda y equals negative 2x. Dividing both sides by 2y, I get that lambda equals negative x over y. So I know that negative y over x equals negative x over y, which means I'm going to have, essentially the negatives would cancel. X squared is going to equal y squared. So when I come back to this equation over here, I can replace either x squared with y squared or vice versa. I'm just going to solve for x squared. So x squared plus x squared minus 18 equals 0. 2x squared is going to equal 18. X squared is going to equal 9. X is going to equal plus or minus 3. Which means that if I come back to this equation again, I'm going to have 9 plus y squared equaling 18. Y squared could equal 9, which means y could equal plus or minus 3. So I'm going to have critical points. I have 3, 3. I have 3, negative 3. I have negative 3, 3. And I have negative 3, negative 3. So I go back up to the original function. 2 times 3 times 3 is 18. 2 times 3 times negative 3 is negative 18. 2 times negative 3 times 3 is negative 18. And 2 times negative 3 times negative 3 is a positive 18. So with that in mind, and with that information, my final answer, I'm going to have maximum value of 18 when my ordered pairs are 3, 3, or negative 3, negative 3. And I'm going to have a minimum value of negative 18 when my xy pairings equal 3, negative 3, or negative 3, positive 3. So those would be my maximum and minimum values based off Lagrange multipliers. If you have any further questions, please bring them up in class. Again, this is our last section of new material, so after this point we'll be trying to finalize some things up. So, take a breath in knowing that this is the last topic, and make sure you're good on this because it will show up on the final.